Lecture problem 3. An object of mass equal to 1.0 kilogram traveling at 5.0 meters per second enters a region where the coefficient of kinetic friction is equal to 0.15. Use the work energy theorem to determine the distance that the object travels before coming to a halt. In order to solve these questions efficiently, the first thing that you need to do is to put together a free body diagram. The box is under three forces: the weight mg, which acts straight down; the normal force acts straight up perpendicular to the surface of contact. This is known as Fn. And since the box is assumed to be moving towards the right, the kinetic friction force has to act towards the left. This is known as Fk. Since the acceleration is parallel to the horizontal, therefore, we're going to choose a system coordinate where the x-axis is horizontal and the y-axis is vertical. Notice that the question is forcing us to use the work energy theorem, which states that the work done by the net force equals the change in kinetic energy. The work that is done by the net force comes from three forces: the work done by the normal force, plus the work done by the mg, plus the work done by the kinetic friction force, must equal the kinetic energy final minus the kinetic energy initial. Notice that the work done by Fn and the work done by mg and the work done by the friction force must be added in a scalar form because the work is a scalar quantity. Since the displacement is horizontal, therefore the work done by the normal force must be zero. A force that makes an angle of 90 degrees with the displacement always does zero work. That's the same thing here for mg. Notice that the mg is pointing straight down and the displacement is horizontal. The work done by the friction force, which is a constant force, is equal to Fk times the displacement d times cosine the angle made between the friction force and the displacement, which is always equal to 180 degrees. That's going to equal the kinetic energy final minus the initial. Notice that the box is going to come to a perfect rest at the end, therefore the kinetic energy final is going to equal 0. As a result, we have 0 minus 1/2 mv initial squared. Notice on the left-hand side of this equation that the cosine of the angle 180 equals to -1. In order to evaluate the friction force Fk, you need to use the dynamics of Newton's laws. The sum of the forces acting on the system of interest equals the mass times the acceleration. There are three forces, which are the normal force, plus the weight mg, plus the kinetic friction force. They all add up to ma. The x component has no normal force, that's 0 because the normal force is vertical. The same thing for the mg, but the Fk has a negative component because it's pointing in the opposite direction of motion. That is going to equal the mass times the acceleration. The acceleration is lined up with the x-axis. The y component will have a positive normal force and a negative mg. Both of them are vertical. The Fk is lined up with the x, therefore has no y component. Of course, the acceleration is lined up with the x-axis, therefore the component of ma along the y is going to be 0. From the y component, we can extract the normal force to equal mg, and from there we can evaluate the kinetic friction force, which equals to mu k times Fn. Substitute the Fn by mg, you obtain Fk to equal mu k times mg. Now let's take this expression and substitute it in our energy equation. Instead of Fk, we substitute that by mu k times mg times the displacement d. The cosine of 180, as I stated earlier, equals to -1. Move the negative sign to the front of the equation. That's going to equal 0 minus, here is the negative sign, 1/2 m v initial squared. Notice that the mass is a common factor, therefore it cancels out. The negative signs are going to cancel out also. Now we can isolate the displacement d by dividing both sides of the equation by mu k g, and the result is vi squared divided by 2 times mu k g. Solving for the displacement d, we obtain 8.5 meters.